of the device. But we left behind two things. One thing is that we made the assumption that each portion of the channel can be treated as an elementary parallel plate MOS capacitor. So I go back to this figure, okay? We extracted the strip of infinitesimal length or width dy and made a calculation on it by assuming that this strip behaves as an MOS capacitor. Now we have to go a little bit deeper into this subject just to understand what type of approximations are involved. So now I go to another figure. I don't know whether it is visible, but I just share it directly. Okay, so this is a zoom into the elementary strip in which we have on top the black portion of the figure is the gate metal. The gray part is the gate oxide. And then we take an elementary portion of the channel of width dy, exactly the same elementary strip as we had in the other figure. The only difference being that it is not necessary to extend the elementary strip down to the bulk contact. It is sufficient to reach the edge of the depleted region, okay? The point is that the edge of the depleted region is not horizontal anymore when we have a current flowing through the device, because due to the application of the drain to source voltage, we also have a lateral component of the electric field. So in the real MOS capacitor by itself, we have only one possible component of the electric field, that is the vertical one, because the device is strictly one-dimensional. In this case, we have two components. So in this figure, we have that the edge of the space charge region is bent. It is the thick line with some slope here, okay? So the depth of the space charge region is xd on the left, and instead it is xd plus dxd on the right. Okay, we assume that they are different and that the depth on the right is larger than that on the left. Somewhere near the interface, we have the inverted charge, okay? It is not indicated in the figure for not to add to the confusion, but of course we must assume that we have an inverted layer at the surface and that the thickness of this inverted layer is h, okay? But it is not very important. So h indicates the thickness of the inverted layer, okay? Now you remember how we calculated the charge in the semiconductor when we were considering the MOS capacitor. we use the cylinders, cylinder 1, cylinder 2, cylinder 3. And in particular, to calculate the charge per unit area present in the semiconductor, we were using cylinder number 3, in which the left face, in this case it is the upper face because this figure is rotated, is very close to the interface. So it is still inside silicon, so we can use the permittivity of silicon, but is inside, very near to the surface. And the other face, the one below in this figure, is in the neutral region, so there is no normal field to it, okay? So if you consider the red boundary, it's the boundary of a cylinder whose axis in this figure is vertical. So we must consider the field at the surface, normal to the surface, and as usual, we call it E sub S. So E sub S is the field in the semiconductor at the surface, at the interface with the insulator. Then we have, in principle, we have another field on the other face, EB, but of course EB is equal to 0 because the lower face of the cylinder is in the neutral region. So EB is indicated, but it is 0. But considering that we have also another field, another voltage applied to the structure between source and drain. So source is on the left and drain is on the right. And of course, in a N-channel device, the drain voltage that is on the right, not visible in the figure, is larger than the source voltage. Okay, so there is a horizontal field that is oriented from right to left. Okay. So when we calculate the charge per unit area inside the red line, we must consider also the field that is normal to the right face, and this is indicated with EYR, that means the component of the field along the Y direction calculated on the right side of the cylinder. And then we have EYL, that is of course the Y component of the electric field, the horizontal component calculated on the left side of the cylinder, okay? And they are represented with the correct orientation. So both of them are oriented from right to left. If these two components, EYR and EY left, were exactly equal to each other, they would compensate exactly, because one of them is oriented inside the cylinder and the other one is oriented toward the external part of the cylinder, okay? So in that case, if EYR is exactly equal to EY left, there is no contribution to the charge from the electric displacement in the Y direction. Okay, so we would be left exactly with the same situation as for the MOS capacitor, but for one exception, that the length of the boundary on the right is a little bit larger than the length of the boundary on the left, because we must consider only the portion of the boundary that is inside the space charge region. So the right one is longer by dxd with respect to the left one. In addition to that, in general, the two components of the field in the horizontal direction are different. So EYR is different from EYL, okay? So the application of the Gauss theorem becomes a little bit more complicated, okay? It becomes two-dimensional. So now the approximation comes into play, okay? First, we neglect dxd. We say that difference in the length of the two vertical boundaries is infinitesimal, so we don't consider it, okay? Number two, although EYR is different in principle from EYL, this difference is very small. Why? Because we are considering only the functioning of the device in the linear region, and in the linear region, we have a very large vertical field because we are applying a voltage to the gate large enough to force the strong inversion condition of the interface everywhere. So the vertical field is large. The horizontal field is small because in the linear region, VDS must be smaller than the saturation value. So it is not so big, okay? So if VDS is not so big, the horizontal variation in the electric potential across the width dy, the variation in the potential is small, and the variation in the field is even smaller. So EYR is almost equal to EYL. We neglect the difference, so we somehow force the two fields to compensate each other exactly in the calculation of the charge inside the red line. So after these simplifications, we are back to the case of the MOS capacitor. Okay, the only difference is that the surface potential at the position of this red line is different from the surface potential in the other locations in the channel, but this was already accounted for during the integration that we have performed during the last lesson. Okay, so this is to show the approximations that are involved in the reasoning, whose outcome is that we essentially treat each elementary strip of the channel as if it was a one-dimensional MOS capacitor. This is it for one part of the approximations. Now we go back to the other approximation. You remember that so we have now demonstrated number one, parallel plate capacitor, and number two, of course, follows because we treat the parallel plate capacitor with the full depletion and Ashe approximation, okay? Now we have to show that the simplification of using the ohmic transport only is correct. And you remember, we demonstrated that this is equivalent to the relation phi s equal to phi n plus phi f. So it is equal to relation number 3. So now we have to demonstrate this relation, but this follows from the same analysis that we already made to demonstrate number 1. You remember what we did was we assumed that the two lateral components of the electric field, one on the right and one on the left, are equal to each other. Okay. This is equivalent to state that the horizontal variation in the electric field from left to right, which means over a length equal to dy over the infinitesimal length dy, is negligible. But the electric field is, apart from the minus sign, is the first derivative of the electric potential. So the variation of the electric field over dy as a consequence is the second derivative of the electric potential with respect to the y coordinate, okay? So number 1, or the reasoning behind assumption number 1, is equivalent to state that the second derivative of the electric potential with respect to y is very small. Okay, so we shall exploit this to demonstrate number 3. Okay, so we go now to this calculation, which is a replica of the calculation that we have already done. So essentially, we repeat the solution of the Poisson equation in the MOS capacitor. We repeat it in the MOS transistor at some position in the channel. So again, we state the definitions and the hypothesis. The hypotheses on the left are that we, of course, we have a two-dimensional situation, so no dependence on Z. We assume that the substrate is uniformly doped of the p-type, so n is equal to minus NA. And we assume the typical boundary conditions that are that in the bulk, the electric potential phi is equal to 0 for each position y. So the infinity is related to the x coordinate. Okay, for each y, phi in the bulk is 0, and also phi prime, that is the derivative with respect to x, is 0. Okay. Now we go to the definitions on the right. As usual, we assume that the majority current concentration, that is the concentration of the holes in the bulk, is pp0. That of the electrons is np0 for every position in the channel. We introduce, as we did already, the normalized electric potential, Q phi over KT, we call it U. But now, since in the MOS transistor we are in a non-equilibrium condition, we cannot use the Fermi level anymore. We must use the quasi-Fermi levels or potentials, okay? So we introduce the normalized quasi-Fermi potentials, UN, UP, and of course the normalization is with Q over KT, okay? And then we remind the definition of the Debye length for the holes, that's the square root of 2 permittivity KT over Q squared PP0, okay? At this point, we consider the expressions of the electron and hole concentrations in the non-equilibrium condition, and we also assume that we are in the non-degenerate condition, so we use the exponentials. So in normalized form, n is equal to ni times the exponential of u minus un. As you may remember, in the equilibrium condition, un becomes uf, that is the normalized Fermi potential. In the calculations, it is preferable to consider the differences with respect to the equilibrium case. So in the exponent, we add and subtract uf. So in the second definition of the electron concentration, you observe that we have ni exponential of u minus uf plus uf minus un. Same thing for the holes. P is ni exponential of up minus u, and then again we add and subtract uf. Okay. Now we introduce the difference between the quasi-Fermi potential and the Fermi potential. So for the electrons, the difference phi n minus phi f is something that we call psi n, and that is, of course, as the units of a potential, and psi n goes to 0 at equilibrium because phi n goes to phi f. Similarly, we define the variation of the quasi-Fermi potential for the holes, phi p with respect to phi f, and then we call this psi p. Then we need the normalized quantities correspond to psi n and psi p. We call them chi n and chi p. And they are, of course, q psi n over kt, q psi p over kt. Again, chi n goes to 0 at equilibrium, and chi p also goes to 0 at equilibrium. But at this point, we remember that the quasi-Fermi potentials do not depend near the interface with the insulator, do not depend on the x coordinate, because we do not have a current, a component of the current vertical that is normal with respect to the interface. So phi n and phi p, and similarly chi n and chi p near the interface, do not depend on x, they depend only on y. In the bulk, they may depend, or actually they do depend also on x. But this doesn't matter because we consider them only near the surface where we have the current of the transistor, okay? After completing these definitions, we simply have to replicate the solution of the Poisson equation. So we simply replicate the analysis already done for the MOS capacitor. There is one fundamental difference, that for the MOS capacitor, the analysis is fully and rigorously one-dimensional. In this case, at least for the moment, it is two-dimensional, okay? Because the electric potential depends on both x and y. Anyhow, we start by writing down the charge density that, as usual, is Q times the concentration of holes minus the concentration of the electrons plus the concentration of the net dopant concentration. Then we remember that in the bulk, the device is neutral. And also in the bulk, U is 0 because of the boundary condition. And chi p and chi n are also 0 because in the bulk we have substantially an equilibrium condition. Okay. So in the bulk, we may write that the brackets that appear in the definition of rho, I mean the quantity in brackets is 0. So we have that n is equal np0 minus pp0. This is exactly equal to what we obtain in the MOS capacitor. So after some calculations that are identical to those of the MOS capacitor, we express the charge density in the semiconductor with minus qpp0 times a function a, and this function is a pure number, okay, no units. And in the equilibrium, you may remember this function a depends on u and uf, the normalized Fermi potential. In this case, it would depend on u, chi n, and chi p. And the explicit form of A is given below. You see, if we replace chi n and chi p with uf, we obtain again the equilibrium expression of A. Okay, and the ratio np0 over pp0, as you remember, is the exponential of minus 2uf, so it is a very small quantity. Given that, we simply write down the Poisson equation, and we have to do it in 2 dimensions, okay, because we have a 2-dimensional problem. So we have the second derivative of the potential with respect to x plus the second derivative of u with respect to y is equal to 2 divided by the square of the Debye length times a. So in principle, we should solve a partial differential equation in the structure, okay? Now we introduce the simplification that we discussed above. You remember, when we are in the condition of a well-formed channel, we have that the vertical component of the field is very large, and the horizontal component of the field is small. So the variation in the horizontal component of the field across the elementary strip dy is negligible. And if you remember the analysis that we have done 10 minutes ago, this is equivalent to say that in the expression of the Poisson equation that is visible in the last line of the page, the second derivative of u with respect to y is negligible with the second derivative with respect to x. Okay, so this is the important simplification that we can introduce when the channel is well formed. On the right-hand side, A still depends on both x and y, because you remember we have the dependencies on u, chi n, and chi p. They still depend on y. We have not eliminated y completely from the equation, but we don't have anymore the derivative with respect to y. The only derivative is with respect to x. So when we eliminate the second derivative with respect to y, we have a one-dimensional differential equation in which y that appears at the right-hand side behaves like a parameter So it changes depending on the position in the channel where we are, okay? There is another simplification that we can introduce. This can already be commented considering the expression of the charge density. When we consider the Poisson equation in the MOS capacitor, we solve it for any value of the applied voltage, okay? So the solution of the Poisson equation in the MOS capacitor is fully general, so it applies in strong inversion, weak inversion, depletion, flat band conditions, and accumulation. In this case here, we are considering only the situation in which the channel is fully formed. So in this case, we have a large and positive gate voltage because we are considering the N-channel transistor. So we have many electrons in the channel, but we don't have practically any holes because the holes have been pushed away from the interface. Okay, so we have just a layer of electrons, and then we have the space charge region in which the charge is essentially due to the dopants. So in the expression of the charge density, we can neglect the concentration of the holes because we are considering the strong inversion condition. So we simply drop, so we simplify the form of A, and this is useful because instead of having chi P and chi N, we have only chi N in the equation. Okay, so this is another simplification that restricts the analysis to the strong inversion condition. Okay, so when we do that, okay, when we neglect the holes, we simply neglect the exponential of chi p minus u. Okay. But also we say that the concentration of the electrons is large. So we expect that the exponential of u minus chi n is large. So we also neglect the -1 in the brackets in the definition of A. Okay. When we neglect the -1 and we are left with the exponential of u minus chi n, we remember that the quantity in front of it can be written as the exponential of -2 uf. So we use this definition so that the expression of A simplifies quite a lot. We have the exponential of u minus chi n minus 2 uf plus 1 larger than 0. Okay? Still, the electric potential depends on u and ny. Instead, chi n, you remember the quasi-Fermi potential near the interface does not depend on x because there is no vertical current, so it depends only on y. At this point, we introduce the simplification on the left-hand side, on the operator, okay? We say the variation of the electric field in the y direction is negligible, so we drop the second derivative with respect to y. We keep only the second derivative with respect to x. So we have an expression for the Poisson equation that is again the same as for the MOS capacitor, which is even simpler because the expression of A is simpler since we are considering only the strong inversion condition. Okay? From now on, we repeat exactly the solution strategy that we implemented for the MOS capacitors. We multiply both sides of the equation by the derivative u prime. U prime, u second is like 1/2 derivative of u prime squared. We integrate over x. Obviously, the right-hand side becomes the integral over the new variable u, because u prime dx is like du. And this integral is by construction positive, because a is positive after the simplifications that we have introduced. A retains a dependence on y because there is chi n in it. Chi n depends on y. So when we have integrated this, us will depend on y. Okay. So in conclusion, if you remember the analysis carried out on the MOS capacitor, after the integration, we find out that the left-hand side is like the square of the surface electric field of the semiconductor ES normalized to Q over KT. And to the right, we have again function capital F in a simplified form, okay, because it is the result of the integration only of the contributions from the electrons and from the dopant. There is no contribution from holes in this expression, okay? So we know by construction that US, the electric potential at the surface, is non-negative, okay? We don't have accumulation. So F squared after the integration has the form visible here. Of course, the semiconductor charge is negative because it is made of the two contributions from the electrons of the inverted layer. Of course, they are negative, and the dopant that is also negative because it is made of acceptors. So in this case, we have only the minus sign. So QSC is minus that coefficient times F, okay? You see immediately that when US is 0, F is also 0. And this is the usual flat band condition that we already commented for the MOS capacitor. Instead, when US is positive, then the charge is negative in the semiconductor, and there is no possibility, at least, okay. We cannot consider US as negative because the calculation has implicitly excluded the accumulation condition. Now, you remember we have another possible expression for the semiconductor charge per unit area, that is QSC is equal to minus C ox times VGB prime minus phi s. And this is fully general because it is obtained from the solution of the Poisson equation on the side of the metal. Okay, so this is always correct. Okay, let's put them together because we have two expressions for QSC. So if we eliminate QSC from these two expressions, we obtain the relation that is visible in the middle of the page. In this relation, we must define the normalized gate to bulk voltage UGB prime, okay? And by equating this expression to the other one, we obtain a relation in which, as you can see immediately, the only unknown is US, if we consider chi-n as given. Okay, so it is possible from this relation to extract US, but it is not actually necessary. Okay, let's just investigate the behavior of this formula. You remember how we defined the threshold condition in the MOS capacitor. The threshold condition in the MOS capacitor is the condition in which, under the square root, the dominating term is the exponential of US. That is, exponential of US times the factor on its left is larger than US by itself. Now, in order to have the exponential prevailing, it must happen that the exponent is positive, okay? And the exponent is US minus chi-n minus 2UF. So when this exponent is positive, the exponential is dominant with respect to US. So the threshold at which the exponential starts being dominating is when US is equal to 2UF plus chi-n. Okay, so this is the generalization of the threshold condition with respect to the equilibrium case. You remember, in the equilibrium case, the threshold is when US is equal to 2UF, okay? In the non-equilibrium case, it is the threshold is given by 2UF plus chi-n, okay? Another observation is this, that assume that you are at threshold. What does it mean? It means that the gate voltage has been selected in such a way as to impose that US is equal to 2UF plus chi-n. Okay, so we impose the threshold condition by controlling UGB prime. Okay, at this point, let's increase UGB prime. Okay. If we do it, we expect that the surface potential will also increase, okay? But this increase is large. Not the increase in US. The increase in the exponential of US is large if US increases, okay? So even a minimum variation in US from the condition of threshold is able to produce a strong increase in the right-hand side of this equation because US is inside the exponential, okay? The same increase must occur also to the left. And this is done because we increase very much UGB prime. So the conclusion of this is when we reach the threshold, if we keep increasing the gate voltage, the surface potential does not increase too much, because even a very small increase of it is able to produce a large increase in the exponential of US, so to compensate the variation of the charge of the left-hand side. Okay, so this is why we, in general, assume that when we reach the threshold condition in the transistor, then the surface potential varies little if we try to increase further the gate voltage with respect to the threshold value, okay? At this point, we remember that chi n is the variation of the normalized quasi-Fermi potential of the electrons, un, with respect to the normalized Fermi potential, uf. So chi n is un minus uf. If you replace chi n in the threshold condition, you find that the threshold condition is just uf plus un. And if you multiply by kT over Q both members of these, both sides of this relation, you find that phi s is equal to phi n plus phi f. That is exactly the condition that we wanted to demonstrate, okay? So this condition applies at threshold, but it also applies above threshold. So in any condition in which the channel is well formed, because of this exponential dependence that we discussed above. So we have demonstrated formally through the solution of the Poisson equation that in strong inversion at each position of the channel, it doesn't really matter where we are, because this applies to every point y in the channel, phi s is practically equal to phi n plus phi f. And from this, if you remember, we also demonstrated that the transport is essentially ohmic when the channel is well formed. So we have completed all demonstrations that were necessary for the elementary theory of the MOS transistor. Of course, we could go beyond the elementary theory. We could consider the sub-threshold condition in which we do have a current, whereas this model assumes that when the transistor is in the sub-threshold condition, it is completely off. This is not true, of course. And there are also more refined theories described in the saturation regime, okay? But we don't have time for that. So we shall continue using the simplified model of the MOS transistor when necessary. Of course, the p-channel is completely dual with respect to the n-channel device, so we are not going to consider it. And this is it for the MOS transistor. So from now on, now we take the intermission in 10 minutes, but from now on, we shall start considering the solid-state sensors. Okay, so we stop now for 10 minutes. Okay, so this is it. Okay, so when we start considering sensors, of course, we must distinguish a large number of sensors that one can implement using solid-state devices. So there is a classification of sensors that is traditional. And the classification starts from this observation. A sensor is a device that acquires an information from the environment about some physical property and provides a signal to the user to tell the user that this property is being detected. So the classification starts by considering that the signals to be detected could be of different type. For instance, electric, or maybe thermal, or maybe chemical, or optical, or mechanical, or magnetic. Of course, this classification is arbitrary, okay, because electric, magnetic, optic, I mean, all of them come from the electromagnetic theory, okay, but it is a tradition to distinguish the possible input signals using these six classes. On the other hand, it is possible for the sensor to provide the information to the user in different forms. Maybe, again, electric, or thermal, or chemical, or optical, or mechanical, or magnetic. So in conclusion, we can place the possible types of sensors according to these categories into the form of a matrix, okay? So if we assume that the rows are related to the input, to the signal to be detected, and the columns to the type of signal that is provided to the user, okay? If you consider the third row and the fourth column, we have here a sensor able to detect chemical properties from the environment and provide the information in mechanical form. Okay. Mechanical form can be an index, for instance, that moves, or the bending of a piece of metal, whatever. Putting all these combinations together, we have 36 possible types of sensors, okay? If we limit ourselves to considering only the sensors in which there is one input and one output, okay? But it is possible to conceive a more complicated type of sensors, like those that have an input signal, an output signal, and a control signal, like a transistor. Transistor is a device in which the input is electric, the output is electric, and the control is electric, okay? But in principle, one may conceive that the control signals also belong to these six possible categories. So In that case, the possible number of types of sensors is 6 by 6 by 6, and so on, and so on, and so on. Okay, so of course we shall examine only a very small number of types of sensors. Okay, by the way, this classification has a name, and the name is written on top of the slide. It's called if you think of a three-dimensional arrangement, input, output, and control signal, you have a cube instead of a matrix, and one can think of this arrangement as a cube, sorry, and the cube is named after Middle Hook, that is a scholar who investigated many types of sensors. Now we start with the optical sensors. The optical sensors are sensors in which we exploit the ability of solid-state matter to absorb visible radiation and provide some type of signal in which, for instance, the intensity of the detected radiation has been coded. In a semiconductor, when we consider the valence and conduction bands, okay, you remember that we already analyzed the optical absorption, okay? The optical absorption occurs when we have a photon. If you look at the left part of the figure, you have a photon that impinges on the semiconductor, and this photon interacts with an electron that initially is in the valence band. And the photon is able to release each energy to the electron, and this energy is enough to force a transition of the electrons from the valence band to the conduction band. This is called absorption because the electron absorbs the energy from the photon. There is another process that is dual to it. It is shown in the middle. It is called the spontaneous emission, in which an electron initially in the conduction band makes a transition to the valence band, emitting a photon whose energy is equal to the energy that is lost by the electron. This is called spontaneous emission. And finally, there is the third possible phenomenon in which an electron that is initially in the conduction band interacts with the photon impinging on the semiconductor, and the photon triggers a transition to the valence band of the electron. And in so doing, the electron emits another photon. If that happens, we talk of stimulated emission, and eventually we have two photons. One photon is the photon that has triggered the transition, and the other photon is the photon that has been emitted during the transition. And these two photons are coherent. They have the same frequency, phase, and direction. So if we succeed in doing stimulated emission in a material, we amplify the radiation. We already mentioned this phenomenon. We also said that solid-state lasers are built on this principle, but we are not going to investigate lasers. We are only going to investigate sensors. So materials in which the majority of the electrons are initially in the conduction band. So the number of absorptions is dominant. And if one electron makes a transition to the conduction band, then it becomes free to move in the material. So in some sense, we can detect an electric current that is related to the number of electrons that absorbed energy from the impinging radiation. Okay, so the current is the way we detect or we see that there is a radiation impinging on the material. The easy way is for creating an optical sensor is simply using a uniform piece of semiconductor. If we use a uniform piece of semiconductor, when there is a light impinging on it, and this light forces transitions, of course we have a larger number of electrons in the conduction band, and at the same time a larger number of holes in the valence band. So we enrich the two bands of carriers. So we expect that if we apply a voltage difference to the piece of material, the current will be larger than in the case where we have no illumination. Okay? This is something that we could do. It is called the photoresistor. It's a very simple device, just a resistance made of semiconductor with two electrons on the two sides. We apply a voltage, we obtain a current, and then if there is light coming in, we see that the current increases. Unfortunately, this is not a very efficient solution because, first of all, we have a current even if there is no light, simply because we apply a voltage. Okay, so we consume power for nothing. Okay. Also, the other disadvantage of the photoresistor is that when the light impinges on it, the current has a variation. So we must detect a variation of the current with respect to the current that existed without illumination. This variation may be not so large, so that we have an issue of noise. Okay, so the signal is not very good. Okay, we have a small variation with respect to the ground current that exists even without illumination. So this device consumes power and is noisy. Okay, for this reason, it is not very much used as an optical sensor. We can improve the situation by considering a photodiode. A photodiode is simply a PN junction. Let me make it smaller. Sorry. It's a PN junction, like the one that is shown on the left. Assume that the switch S that is visible in the figure is closed. So we apply a voltage V0, And this voltage V0 is negative. So the photodiode is biased in the reversed, with the reverse bias. Okay, so if there is no light, we have a small current in the device. Then assume that there is some light coming in. If you look from the top, you see that these white arrows mimic the impinging light, okay? So of course the metal contact must be on the side. So the larger part of the upper surface of the device must be free. Otherwise, if we have a metal on top of the device, on each position in the device, if we have a metal contact, most of the radiation would be reflected. Okay, so we need to consider contacts that are small and have the largest part of the upper surface of the photodiode free from contacts. So we have photons coming in. The photons enter the device, and you remember well, but we shall see it in a second in another slide, that there is an absorption, and this absorption has an exponential form. So the flux of photons decreases exponentially in the material. For this reason, it is necessary that the neutral region on the P side of the junction, that is the side on top of it, okay? This neutral region should be very thin. Why? Because when the photons enter the device, they start crossing the neutral region of the p-type, and they produce, by optical generation, they produce electron and hole pairs, okay? These electrons and holes, if we consider the neutral region of the p-type, are in a region in which the electric field is negligible, okay? So they move, but they move by diffusion. And while they move, they recombine, okay? Because there is an excess of electrons and holes. And you remember that when there is an excess of electrons and holes, and they diffuse parallel to each other, okay? They recombine. So the optical generations that occur in the neutral region on the upper part of the device are lost. They are absolutely of no use for the purpose of detecting the light, okay? And there are many, because the exponential decay of the flux has just started, okay, because we are near the surface. The only possible solution to this is that the neutral region of the p-type must be very thin. So we need a very shallow junction. The junction must be very close to the upper edge of the device in order to limit the extent of the neutral region of the p-type. Then the photons, after crossing, the photons that survive the absorption in the neutral region of the p-type enter the space charge region of the junction. And also in that region, they continue to generate electron-hole pairs. But in the space charge region, there is a strong field. And since the applied bias is reversed, that is V0 is negative, the holes generated in the space charge region are attracted to the upper part of the junction and the electrons are pushed to the lower part. So the pairs are separated. You see the symbol EH with the two arrows. That symbol means that the electron hole pair, as soon as it is generated by a photon, the hole goes up and the electron goes down. So these two carriers do not recombine, but they contribute to the current. At some point, if there are still photons surviving the absorption, these remaining photons enter the neutral region of the n-type. And again, they are lost. They are useless because they produce generations in the neutral region again. So these generations are useless, okay? So in order to avoid this, we must have that the edge, the lower edge of the space charge region, the one that is indicated by the arrow Ln on the left, this edge must be very low in the device so that the large majority of photons is absorbed in the space charge region, okay? To achieve this, we must have that the space charge region must be very large, and this is possible only by doping, by introducing a very asymmetric distribution of doping. So the P region must be heavily doped, and the N region must be lightly doped. Thanks to this, we have that the extension of the space charge region is very large on the N side. So we have a very large space charge region. And thanks to the asymmetry, also the position of the junction xj, as indicated on the left in the figure, is very shallow, is very near to the surface. So we minimize the number of generations in the neutral region of the p-type, and we maximize the number of useful generations that are those that occur in the space charge region. Obviously, the optical generations, those produced by the photons, produce a current, and this current adds up with the thermal current produced by the current that would be present in the device if there were no photons around, okay? So why is this device better than the photoresistor? Because since the saturation current of the PN junctions is small, the additional current produced by the photons is large with respect to the current that is present in the device when it is kept in the dark, okay? So for this reason, we have a much better signal to noise ratio in this device with respect to the phototransistor, okay? In the figure, you can see that at the bottom of the figure, there is a resistance, okay? This resistance is simply the symbol for the input resistance of anything that is attached to the photodiode. Okay. If we want to detect the current of the photodiode, we must attach something in series to the photodiode itself in order to detect the current. We mimic whatever it is with the equivalent input resistor that we call R. So R is just the equipment that detects the current. Okay. So when we keep the switch as closed and we have a constant voltage applied to the photodiode, we essentially have a current that is produced in the circuit. It crosses the photodiode, the resistance, and the external circuit, okay? And we measure this current. And this current, apart from the inverse current, saturation current of the photodiode, is a useful signal that we can detect. When the photodiode works in this form, we say that it works in the continuous mode, because we keep, at each instant, we keep detecting the current, okay? It is an improvement with respect to the photo resistor, but we can do even better, okay? For the moment, let's make a little calculation relative to the photodiode working in the continuous mode, okay? We simply solve the continuity equation for one of the two possible colors. For instance, we use the holes, okay? So on top of the page, you see the continuity equation for the holes. In the usual form, we have the derivative of the hole concentration plus the thermal net recombination plus 1 over Q divergence of JP. And at this point, we must add to the right-hand side the optical generation, okay, that we never considered before. Then we assume a one-dimensional condition. As usual, we take the x-axis normal to the surface of the device. Okay, so in the figure, the x-axis is vertical. And we assume the steady state condition of the device, okay? It is not really necessary to completely solve the model of semiconductor devices, okay? It is sufficient to the purpose of calculating the current. It is sufficient to use this equation and integrate this equation over the space charge region. You remember that the edges of the space charge region, the thin line here and the other thin line below, okay, in the theory of the p-n junction, they are called O minus, the one on top, and O plus, the one at the bottom, and the x-axis is oriented top down, okay? So we integrate the continuity equation from O minus to O plus. And we make another observation that the holes, as soon as the holes are generated, they are oriented by the field and go upwards. Okay, so the holes go upwards, and the edge O minus will be crossed essentially by holes. Instead, the electrons are oriented by the field towards the lower edge O plus. Okay, so there are many holes at O minus and not so many electrons in O minus because the electrons go down. So when we calculate the current of the holes, the only contribution to the hole current will be given at O minus, okay, because there are practically no holes crossing O plus. So when we integrate the equation, first we multiply by Q, okay. In one dimension, the divergence is the derivative. So when we integrate the derivative, we have Jp of O plus, but this is 0 practically, as we remember, minus Jp of O minus. So the only one that survives is Jp of O minus. And this is equal to the integral from O minus to O plus of G minus U, okay? Now, you remember that the optical generation decays exponentially when we enter the material. So let's assume a monochromatic radiation, which is not true, of course, but for the moment we assume a monochromatic radiation. So we have just a fixed absorption coefficient K. Okay, you remember that G is proportional with the constant G0 to the exponential of minus Kx in general, okay? Here we have minus Ks plus X. Why? Because in this structure, we are assuming that the 0 coincides with O minus, okay? So the photons have already crossed a piece of semiconductor. So we had an absorption in the initial region of the semiconductor, and this absorption is lost, okay? So how long is the initial piece of the semiconductor? It is equal to the neutral region of the p-type, whose length, as you can see from the symbol, is xj, the junction depth, minus Lp, okay? So for this reason, we account for this loss of photons by this factor exponential of minus Ks, in which S is equal to the junction depth minus Lp. Then the coefficient G0 times exponential of minus Ks is called Gs. Okay, so we simply modify the constant in the expression. Okay. Then we have U. U is the net recombination term in the depleted region of a junction that is reverse biased. Okay. So we can assume the full depletion condition. And you remember that in that case, U takes one of the two possible limiting forms, the form of full depletion. So U is equal to minus the intrinsic concentration divided by the generation lifetime tau G. Okay? Finally, you remember in steady state and one dimension, the total current is equal to the sum of the hole current and the electron current at the same position, for instance, O minus. But from the discussions that we had 1 minute ago, we remember that at O minus, the population of the holes dominates. So the current is essentially due to the holes. So Jp of O minus is practically equal to J. So we replace it here. We have minus J. Then we must integrate the optical generation. Of course, we get Q times Gs over K times 1 minus the exponential of KL. Plus the term associated to the thermal generation, that is plus Q and I over tau G L. L, as you remember, is the extension of the space charge region of the device. Now, we can make an estimate. If we take a monochromatic radiation that is in the center of the visible spectrum, okay, that is, the color is green, okay, green corresponds to a wavelength of half a micron. When we have this wavelength, the corresponding penetration length, that is the inverse of the absorption coefficient, turns out to be 1 micron. Okay, so 1 over K is 1 micron. So K is 1 micron to the minus 1. It is very easy to have a width L that is several microns. Okay, so we have that the product KL, okay, is significantly larger than 1. Okay, so the exponential here can be neglected because KL, we can always obtain this because L is very large on the n side, okay? So we neglect the exponential, and the optical contribution to the current simplifies to QGS over K. This is very good because QGS over K does not depend on the bias, on the voltage drop across the junction. Instead, L does depend on it. Okay, so we eliminate any influence of the bias. Then we have the other term that is still there, Q and I L over tau G, okay? Now, in practical situations, if the semiconductor is very good, that is, there are not so many defects in the semiconductor, then tau G is large, okay? So this fraction is expected to be small. And if there is enough illumination, GS, you remember, is proportional to G0, and G0, you remember, is the flux at the surface of the semiconductor immediately inside the semiconductor surface. Okay, so if there is a large illumination, GS is large. So it is written below, okay? Hn phi 0, that is the flux of photons. Hν is the energy of the photons. Phi 0 is equal to G0 divided by the efficiency. The quantum efficiency is near 1, and K. Okay, so substantially we can assume that this term is dominant. Okay, so we have that J is practically proportional to the flux. Okay, which is very good. It is a very simple solution to the problem. The current of the device is the current density multiplied by the cross-sectional area of the device, okay? And we have a good improvement with respect to the photoresistor, okay? Now the point is, can we improve further? Can we expect to manipulate the device in order to obtain an even larger current? The answer is yes. We can improve the device if, instead of having the device functioning in the continuous mode, as we did so far, we force the device to work in another mode that is called the storage mode. Qualitatively, the storage mode functions as follows. We open periodically the switch. So assume that at some point we open the switch. When we open the switch, no current can flow through the device because we have opened the external circuit, okay? So we have a device in which no current can flow, but light keeps impinging on the device. So we have a device in which the optical generations continue to happen, but it is impossible for the generated charges to flow through the external circuit. The conclusion is that the generated charges, electrons and holes, accumulate inside the device. We shall see soon how this happens, okay? This accumulation is also called storage. For this reason, this type of functioning of the device is called the storage mode. The interval of time during which the switch is kept open, so where the storage takes place, is called the integration time, because it is like we are integrating the charge inside the device. When the integration time is finished, we close the switch. Okay? When we close the switch, a much larger amount of charge with respect to the case of continuous mode flows through the external circuit. So we have a much larger amount of charge because it is the charge that had been accumulated inside the device during the storage period. This charge all of a sudden flows into the external circuit. So we have a much larger current flowing through the external resistor. And of course, a much larger current provides a much larger voltage across the external resistor, okay? So we can detect a much larger current because it is the current, sorry, a much larger charge because it is the charge accumulated during the integration time. For how long should we keep the switch closed? The time during which we must keep the switch closed is the time that is necessary to restore the initial conditions in the photodiode. And this time is non-negligible, because if we don't restore the initial condition, if we start another integration too early, there will be charge left behind from the previous integration. So the new charge that is integrated will add to the old charge, and the signal will be polluted by noise, okay? It will be a wrong signal, okay? So the interval of time during which we keep the switch closed is called sampling time and must be long enough to restore the initial condition in the device, okay? So why is this storage mode better? Because one may say, yes, it is true, we have a much larger signal from the device, but we obtain this signal only from time to time, okay? We obtain the pulse of current only with the period that is the sum of the integration time and the sampling time, okay? So we don't have a continuous description of the light impinging on the device, but only we have an information from time to time. So somehow we are losing something, okay? We are losing the continuity of the information. We can live with it. Why? Because assume that we are using a matrix made of photodiodes to form the pixel of a sensor that controls a video of a TV set, okay? You know that the signal in a TV set is not shown continuously, okay? It is shown frame by frame. And each frame takes some tens of milliseconds to be completed, okay? The human brain detects a succession of frames as if it is a continuous signal if the frames are presented with a sufficiently high frequency. That is, the distance in time should not be larger than 50 milliseconds, okay? So if we operate the matrix of photodiodes within the limits of these constraints due to the ability of the brain to retain the images, okay, we actually lose nothing. We have a much richer signal and we do not detect the fact that actually there are frames presented there are static frames presented one after the other instead of a continuous signal. So the storage mode is actually a very good improvement with respect to the continuous mode. For now, we are finished, but we shall continue in the description of the storage mode tomorrow. So for the moment, we stop here.